Hello, I'm Professor Steve Miller. Today we'll be continuing our lectures on hypersonics. In particular, we'll be looking at hypersonic heat transfer into the body and estimating this quantity. Then we'll look at the effect of leading edge bluntness. You'll notice that in some hypersonic vehicles, instead of having a sharp point at the leading edge, they'll have a rounded tip. And this is, of course, for a lot of different reasons, which we'll discuss. And then we'll look at particular shockwave interactions in hypersonic flows. Let's get started in this shorter class. Let's start with a quote by Dr. Sion. An engineering science aims to organize the design principles used in engineering practice into a discipline, and thus to exhibit the similarities between different areas of engineering practice and to emphasize the power of fundamental concepts. In short, an engineering science is predominated by theoretical analysis and very often uses the tools of advanced mathematics. Let's look at the subject of hypersonic heat transfer. And remember, heat transfer is the study of how energy is moved from one medium to another. Here's a few important points regarding heat transfer. First of all, we can look at the drag, which ultimately shows up as heat. The drag in the vehicle increases heat. As drag goes up, the heating goes up. Here, we want to try and quantify how heat transfer depends on drag. Now remember, work can be done over very short or long periods of time. Of course, if a vehicle goes faster, we could expect that the work done by the vehicle is much, much higher over a short time if it's going very fast. So we'll try and calculate the viscous heating for a boundary layer, which of course is the predominant mechanism of heat transfer into the vehicle. Now, Newton's first law can be applied to an object deaccelerating in an atmosphere at hypersonic speeds. And we might write that as W, which is the weight of the object, G is the gravity, V is the flight velocity, and of course D is the total drag. So we can write W over G times dV dt equals negative D. Try this out for yourself. It's really dV dt equals negative dWg rearranged. And we can also define a heat transfer coefficient C bar sub H. Here, we'll say Q is the heat transfer to the object, rho is the atmospheric density, S is the area of the object exposed to high temperature gas, and delta I is the enthalpy potential regarding the temperature difference, resulting in heat transfer from hot gas to the cooler aerodynamic body. So here we might say the heat transferred, Q, the rate of change of it, goes as the heat transfer coefficient times some density times Vs delta I, which we've just defined as parameters. So we have two major equations now. Now we can define a delta I equals I infinity minus I sub W, where, remember, I represents an enthalpy potential. Here, I sub infinity is the stagnation enthalpy, and IW is the enthalpy of the air mixture of the object's surface temperature. And so this is really the difference due to, of course, the aerodynamic forces around the body and the aerodynamic motion. Let's further define the enthalpy of the air mixture at the object's surface, and we'll call that T, which is temperature, of course. And now we can relate enthalpy through temperature. In this case, we don't just write, say, H equals C sub P. Here, I is enthalpy in this hypersonics community. So I sub W at the wall will go from 0 to T infinity of C sub P times dt. Here, once again, C sub P is the specific heat at constant pressure, and again, T infinity is the ambient temperature, and T is the temperature of, say, the gas near the wall of the vehicle. And we can't just have a linear relationship, because of course C sub P is changing with temperature. Now, the heat transfer rate will be dependent on the body geometry, density, flight altitude, and velocity, and many other properties of the atmosphere. And we've talked about this at length in the class, so I don't think this should come as any surprise. Slender bodies versus thick bodies will have different properties, and we're trying to explore those to these relations. Now, we want to look at hypersonic speeds in particular, so you should know that our Mach numbers are large, and therefore we can approximate, say, U squared over 2c pt infinity might go as gamma minus 1 over 2 m squared, which will of course be much greater than 7.2 for gamma 1.4 for large m. Here m might be approximating the Mach number in 735 as U squared over gamma RT infinity. We can now note that the temperature on the wall will be on the same order of magnitude as T infinity, and therefore we might write that the change in enthalpy will go as, of course, the kinetic energy. Here we can argue that the coefficient of heat transfer is proportional to the skin friction coefficients and CDF. the coefficient of drag of the skin coefficient. So we make this approximation. We can now combine our two laws with these assumptions on the last page from Newton and heat transfer, and we can write dq, the change in heat transfer, or change of heat, is negative half of the drag friction divided by the coefficient of drag times d times w over 2g times u squared. Here we'll approximate drag d in this equation 739. It's just an approximation. We'll say there's a drag due to the stresses. Will go as the coefficient of drag times rho u squared times s over 2, where s is like some cross-sectional area. We can now integrate this equation for q sub f in, of course, 738 with this approximation of drag, and we'll find 740. So qf with a subscript f will denote the final value of the heat transferred to the body. So q sub f is the whole heat transferred into the body after it has converted all its kinetic energy into heating of the body, and I will denote the initial value, the sub I, u sub I. So that could be like the initial value of return to orbit into the atmosphere. That's its first initial high velocity. So you can see this indeed goes as the square of the velocity. And so, of course, higher velocities will result in higher heat transfer if the vehicle is brought to rest through aerodynamic forces. Now we can assume as a first approximation that just say, for instance, that u sub f, the final velocity is 0, and the initial heat into the body is 0. Then therefore you can see that the heat transferred to an object decelerating at hypersonic speeds within the atmosphere is indeed proportional to the product of the kinetic energy, which is the ui squared term, and the ratio of the friction drag coefficient to the total drag coefficient. So we'll try and minimize CDF over CD to lower heating, which is this term. We cannot change a half, we can't change the second half, we cannot really change W, and we can certainly not change G, because it depends on the planet we're near. And we may not be able to change U, except for maybe early deceleration burns before our vehicle comes to the atmosphere. But generally we can't change U. All we can really change is CDF divided by CD, which is a function of the vehicle geometry and, of course, some of its properties. Let's try and explore this equation more. We'll graph it. On the x-axis, we'll have the initial velocity u sub I. Here we'll call it v sub I. And that'll be in 1,000 feet per second increments from 5, 10, 15, 20, 25, 30, and 35. For example, the last unit is 35,000 feet per second of a re-entry velocity initial into the atmosphere. The y-axis is q, which is BTU in pounds. So that's the heat transfer into the body per pound of the body weight. And here we plot several aerodynamic values, which are, of course, CDF over CD. You can see here's a flat plate, here's a streamlined airplane, and here's a very, very thin body. Ideally, we can convert all the kinetic energy into the body heat. We'll find this particular asymptotic curve. Everything above this curve might be impossible to achieve in actual flight and aerodynamics because these solutions don't exist. Everything down here, of course, are possible solutions. So this is an asymptotic value. You can never have more heating than this particular line for these values of G and W for the particular aerodynamic body. So typically in most vehicles, we'll find, say, a CDF over CD of 0.01 for a sphere, 0.33 for a streamlined airplane, and maybe 1.0 for a flat plate. We'll see that the total heat transferred indeed can exceed the heat capacity of most known refractory materials. And so if we know the weight and mass, and we know how much heat goes into it, we can find the temperature using basic thermodynamics and estimate if our material will fail or not during re-entry into the atmosphere. Let's look at some known values of these aerospace materials just so you can get an idea. On the left side is a column of, say, tungsten, tantalum, zirconium, molybdenum, titanium, silicon carbide, magnesium oxide, beryllium oxide, and of course graphite. Here's the total heat capacity from 312 Kelvin through vaporation in Kelgram. In the right column, we show total heat capacity from 560 Rankine through vaporation in BTU pound. Let's focus on the middle columns. I prefer SI unit. You can see a typical aerospace material like titanium will have 2145 Kel per gram before vaporization from an initial temperature of 312 Kelvin, which is basically like a warm room temperature. Now, the theoretical maximum heat capacity of any material is absolutely never realized in applications for the type being discussed due to, of course, non-uniform heat distribution. And so we can carefully design our vehicles to dissipate the heat through different mechanisms. Our analysis will show that blunt and non-stream objects are to be used if high amounts of heat are to be avoided. That's, of course, so that we can dissipate the heat away from the leading edge of the vehicle, like we showed in the movies of, say, melting cones in our previous classes and, of course, online discussions one-on-one. Now, a sphere might serve as such an object which is non-blunted and have its large radius of curvature. And this is why a lot of hypersonic vehicles use, say, spherical or large radius of curvature nose tips to sort of dissipate away that heat from the sharp point in the vehicle. If, on the other hand, we might streamline the object or aerospace vehicle or reentry vehicle, it might result in excessive high heat temperature rates. And, of course, this could be compromising and make a compromise between the heat protection system and, of course, the aerodynamic efficiency of the particular object to reduce this heat buildup in the leading edges. Let's look at some examples now of these particular vehicles. Here's one reentry vehicle, which was tested in a ballistic range by the Avco Corp in the form of a shadow graph. Remember, a shadow graph is where we send beams of parallel light towards, say, a white piece of paper and take a picture of the shadow that's cast by the vehicle. And so, of course, here the camera is taken behind the shadow graph. Here we can see a large turbulent wake. We see the vehicle itself is in black, and we have a reference line of where it's taken with respect to the camera. Here we see the blunt leading edge, which you can see is indeed a constant radius of curvature. There's particularly strong oblique shock waves coming off the vehicle. Now you can see in this case the nose of the vehicle is blunted in order to reduce heat transfer rates in that region. You also see that it creates always a strong detached oblique shock wave or bow shock, which we discussed in the previous classes. The aft frustrum of the vehicle, which is the portion of the cone or pyramid that remains aft of its upper part, has been cut off by a plane parallel to its base, in that it's intercepted between two such planes. And this provides aerodynamic stability. Let's look at that in the previous photo. You can see here's this initial cone, which comes back to a cylinder and brings back again another turning angle. This is done for aerodynamic stability of the vehicle, which is another subject of hypersonics, of course. Now, the majority of the heating occurs in the thin viscous boundary layer next to the body, as we discussed earlier in the class. Remember, there's a large entropy or temperature layer, which is much hotter than the actual skin temperature. But this affects the heat transfer rate. And really, we only care about the amount of heat transferred or the heat transfer rate into the body. By keeping the heat transfer rate down, we can, of course, lower the vehicle temperature by having an active cooling system in the skin of the vehicle. Now, we'll try and concern ourselves with the problems associated with heating of the leading edges, because this is, of course, one of the most difficult problems and one of the highest heating effects. So we'll try and derive some equations for the effect of the interaction of the leading edge shock and the boundary layer upon the skin friction and heat transfer. This boundary layer has a displacement effect in the sense that the shape of the body is altered or enlarged because of the reduced mass flux in the boundary layer. We'll call this displacement thickness delta sup star. That's the displacement thickness of course, the boundary layer flow. Let's do some analysis now to understand this. We'll say rho E UE times delta minus delta sup star, which is boundary layer thickness minus displacement thickness. The sub E denotes the value at the edge of the boundary layer. We'll say that goes as the integral of 0 to delta of rho U dy. So this is a very simple and basic boundary layer equation, which we discussed way back when we talked about fan of flow when we discussed the simple turbulent boundary layers. Here we're integrating from rho U over y from 0 to delta, which is the, of course, boundary layer thickness. We can then solve for displacement thickness delta sup star from equation 741, and we find 742. You'll see that in the hypersonic turbulent boundary layer, the temperature of the wall is always much greater than the ambient temperature due to the aerodynamic heating and the viscous effects causing the kinetic energy to be converted into, of course, temperature, heat. And the displacement thickness will approach delta for these particular speeds. Now the pressure and Mach number at the edge will also vary with, say, the downstream distance, which is parameterized with the variable s, as if they were replaced by a shape defined by the boundary layer edge. So here s represents the boundary layer edge, this line represents a shock wave, and this is perhaps an aerodynamic body, which we just show as a flat plate for illustrative purposes. In front, we have a large Mach number, pressure, temperature, and ambient density. Here, we can approximate the boundary layer thickness as approximately the boundary layer displacement, which of course goes as the boundary layer edge. Of course, in reality, this is not a good approximation, but they are of roughly the same order. Now, for two-dimensional and for similarly 3D objects, m infinity, of course, is much larger than 1, and therefore m infinity d delta sup star over ds would be much, much smaller than 1, because of course the rate of change of the displacement thickness is much less than 1 as we move downstream. Therefore, we can write the pressure, the static pressure at the edge of the boundary layer divided by the ambient pressure might go as 1 plus gamma m sub infinity d delta sup star ds plus gamma times gamma plus 1 over 4 of m infinity d delta sup star over ds squared plus higher order terms. This is, of course, nothing but an expansion, which we're going to be cutting off higher order terms. You can see for very, very large Mach numbers, then therefore, m d delta sup star ds must be much larger than 1. And using the oblique shockwave relations, which we previously developed, we might write 744 by replacing the pressure ratio on the right-hand side with, of course, these terms here. Now, unfortunately, Pe over P infinity is also dependent on delta sup star, which is a whole problem in the analysis, and we can't go forward very easily. Now, for laminar boundary layers, which definitely occur in hypersonic applications on reentry, because of course the atmospheric turbulence is low at high altitudes, and after the leading edge shock wave, we might write delta sup star squared goes as mu s over rho bar ue. Here, rho bar and U bar are nothing but the average quantities. That is, we're time averaging the quantities of velocity and density at any particular point in space. We may now approximate UE as U infinity and P bar as PE. And we can write the equations as, from 744, given the laminar boundary layer assumption, as delta sup star squared goes as C m infinity to the fourth times P infinity over PE times S squared over R infinity. Here we introduce the Reynolds number based on the ambient values and some characteristic length scale. We can then write d delta sup star ds, that's the growth of the displacement thickness with along S, which is the distance from the leading edge on the boundary layer edge, will go as delta sup star over S approximately. Now, from this analysis, there'll be two particular extremes: the weak interaction case and the strong interaction case for m infinity d delta sup star ds, which would be much less than 1, and the opposite case, which would be much larger than 1. So there's two particular results which we need to understand. For weak interactions, Pe over P infinity minus 1 will go as, say, capital theta bar. And for strong actions, we'll say Pe over P infinity goes as theta bar. Here, we say theta bar is a non-dimensional parameter of c to the half times m infinity cubed divided by the square root of Reynolds number, which can be seen in 746. So we have three major conclusions from this particular mathematical analysis for blunt objects in hypersonics. The first is we have shown and developed for laminar boundary layer flows over the initial part of the hypersonic vehicle. Of course, they transition, but initially they're laminar. That theta goes as c to the half m infinity cubed r to negative 1/2. This is a similarity parameter of hypersonic leading edge shocks. For strong interactions, the displacement thickness will go as s to the 3/4, where s is the distance from the leading edge. And for strong interactions, Pe over P infinity will go to s to the negative half. These relations will hold for all similarity solutions beyond the boundary layer and is valid between the boundary layer and, of course, the shock front. We can now look at heat transfer coefficients with surface temperature for the strong interaction case, which, of course, is what we're interested in for hypersonics. On the x-axis, we have the ratio of the wall temperature to the stagnation temperature in the flow. And on the y-axis, we have heat transfer coefficient. You can see for values of gamma 1.4 and 1.677 the variation. Let's take a few seconds to look at the leading edge bluntness upon the pressure distribution of an inviscid flow over a flat plate. Here on the axis we have S over T, which is a parameterized distance, divided by m infinity times the drag coefficient. The y-axis is P over P infinity minus 1. And so we're plotting the parameterized value S along the distance downstream. T is the thickness of the vehicle, and we're high speeds. We plotted this value non-dimensionally along the x-axis as a power. The y-axis is the pressure along any particular value divided by P infinity minus 1, which we showed in our earlier analysis. And now for measurement, we can plot this data and see how it collapses along a single curve, which is the so-called first-order blast wave theory curve, which is this dashed line down this the log-log curve. And we plot lines of these values for this non-dimensional device at Mach 40, 20, 12, 6.86, and 5. You can see they all collapse along this dashed line, which is the power of this non-dimensional analysis. In this class, we briefly looked at the ideas of hypersonic heat transfer, leading edge bluntness, and the shockwave interaction problem, and we showed particular collapse through one non-dimensional number and helped explain why it's advantageous, of course, due to heat transfer reasons and keeping temperature low on our hypersonic vehicles. Thank you very much for your time today. I'm Professor Steve Miller.